a set omega C is called simply connected. Connected if and only if any two curves with the same endpoints same endpoint that are inside omega are homotopic. Okay, and that in the most rough, in the crudest sense, just means that the thing doesn't have any holes. So if we have a donut shape like this, then there's no way that these two curves are homotopic. We just can't deform one smoothly onto the other without ever leaving the set or having some kind of discontinuity. Yeah. But if you don't have that, then you're in good shape, right? So if you have a set like this, a set of a simply connected set. Because if we have any two curves inside this with the same endpoints, we can indeed smoothly deform one onto the other. Yeah? So, for things like this, we can now do the general theorems of complex analysis. Previously, we've been carefully talking about sets that are delta good, which meant that if we took a collection of squares I, so previously we had we said omega was delta good, no, dyadic good. If omega was the union of a bunch of squares of some size, qi, where if we considered the union of all these guys that weren't inside this thing, qi, then this is connected and unbounded. And all this does is it just prevents you having a set which contains something in its interior, like a hole, right? So this is a crude way of saying you have a set that doesn't have a hole. Yeah? So these things are simply connected sets. But now with this notion of homotopy, we don't have to define it this way. We can define it in a more subtle and more general way. And the point about this is that all the stuff that was true previously for this dyadic good sets are now true for simply connected sets. So the main theorem is that, suppose, oh, I should put the theorem right up here. Theorem. F is holomorphic on a simply connected set. Then F has a primitive. i.e. every, oops, i.e. f prime is equal to f omega. Okay, so I'm going to erase the board. In the meantime, you think about how we can prove this. So what did we prove before? It was a homework exercise for you. We proved that if we have a dyadic good set, then this was true, right? And what was the main steps to do that? What was the main thing we had to think about to be able to achieve that? Yeah? Think about that, and then tell me why it's actually true if we're simply connected. Okay, so proof. Why is this true? Yep, exactly. So if we pick any point we like, say z0, yeah, then we're going to define L of z to be a path that connects z0 to z, wherever z is. So like this, right? So this will be L of z. Yeah? And this is obviously not unique. We can have different path that does this job. Maybe this path is a little bit exciting. It does this. Right? We can have a different path, yeah? But these paths, by definition, are homotopic. They're homotopic driven. We can smoothly define one to the other, yeah? Which by the previous theorem means that any integral we define on these paths will be the same, yeah? So pick z0 inside our set omega, and let L of z be any path that starts at z0 and ends at z. And then define capital F of z to be this thing, to be the integral of L of z of little f of w dw. Okay? So, by the previous theorem, this is well defined. It does not depend on a particular choice of path L. Okay, so we at least have a well-defined function. All right, someone else. How do we go forward? How is this helpful? Why is it the case that this thing is going to be the antiderivative? Let's blow up what happens here. Okay. Let's blow up to this big picture. So this is Z, this is our path coming in like this, yeah? So why is it the case that capital F is the primitive of little f? Okay, let's see what happens if we move off little z by a little bit. Suppose we move up here. This is z plus h for some small number, yeah? So capital F is the same well, capital F of z plus h is what happens when we take any path that goes in and reaches z plus h, right? Yeah? So it's the same for any path that does this, right? Yeah? And what we're going to be considering, of course, since we want to find the derivative, so we consider capital F of z plus h minus capital F of z, yeah? And we're hoping that when we divide this by h, it's going to tend more and more to just little f, right? Okay, now look at this. Look at this and look at the picture. What is this on this picture? Right. Yeah, because this is true no matter what path comes to reach z plus h, right? It doesn't have to be this one, and it's most convenient if it isn't this one. Let's take the path that exactly follows the path that went to z, and let's just extend it up in a straight line up to h, right? So let's take the path that goes up like this, like this. Yeah? And by the theorem, this is a perfectly good path, right? This thing does it, yeah? So when we look at this thing, yeah, all this becomes is just the integral over this line segment, z to z plus h of little f of w dw, right? Previously, we did this by applying Cauchy's theorem on a triangle over and over again, but now we have a more direct thing to do, yeah? Everybody with me here? All right. Now, why does this make you so happy? Why is everybody jumping up and down? All right. If we just look at this expression, yeah, this is just given by this. Over h, right? And this thing, as we look at this expression pretty closely, look at this. If we look at integral of z plus h of f of w dz, let's subtract from that just, say, f of z times h itself, like this. Then what is this? This thing is the same as this. Yeah? So put up some value signs around this. Yeah? And then this is less than or equal to this thing. Right? And then this thing gets very small because f is continuous. Yeah? And we're just going on this little tiny interval of length h, right? So this is less than just the length of this path, h, times the supremum over this interval z plus h of f minus f of z. Yeah? So when we take this expression minus f of z, so capital F of z plus h minus capital F of z over h, you know, minus just f of z itself, right? So it's going to be this thing minus just z. So if we divide h through this expression right here, yeah, we have exactly what we want, and then this h here will just vanish over on this side, right? So this thing is less than just the supremum of f minus f of z over this little strip right here, which will go down to 0 as h goes down to 0. Yeah? Everybody with me? And that's the same thing we did before, right? So this part of the argument it's the same thing after we've reduced it down to going up this straight line segment by using Cauchy's theorem on a triangle, right? So once we're in a little tiny ball, then it's an entirely local argument, and it doesn't notice whether we are in a simply connected domain or a dyadic good domain or anything, right? So this part is exactly the same argument. The only part which was new, the only part was different, was that now we have the right to define this in a well-defined way, no matter what z we have inside our simply connected domain. And the key point is simply connected is a wider class of functions. A wider class of domains. Yeah? Cool. So this is not particularly hard. It's essentially just using the definition of simply connectedness and the main theorem we defined before, which allows us to define this. But then this has all the cool consequences that we garner, right? So for any simple closed curve, gamma in a simply connected domain omega we have that the integral of gamma f of c dz equals 0 for any holomorphic function, right? Because we have a primitive, yeah?